A 28-ton wing is flying through the sea off the Faroe Islands right now, swooping in figure eights on the end of a tether, and it is already powering around 1,000 homes from a current no machine has been able to use until now. It is called the Dragon 12, built by Minesto, a Swedish firm spun out of the aerospace company Saab. The trick is that flying the wing across the current makes it travel several times faster than the water itself, which multiplies what its small turbine can generate. And that single mechanism opens up coastal waters that the tidal industry had written off as too weak. And it does it with the one thing solar and wind can never promise: output you can predict years in advance. In this video, we are going to trace how a slow current of water becomes usable electricity, look at what a kilowatt hour of it actually costs, and face the open questions about surviving the sea and sharing it with marine life. Every grid built on solar and wind runs into the same wall. The power arrives when the weather decides, not when you need it. So operators have to keep expensive backups ready for the moment a cloud bank rolls in or the wind drops. And the more of these sources you add, the harder and costlier that balancing act becomes. But tidal power does not have that problem. Tides are driven by the gravitational pull of the moon and the sun, so they run on a fixed astronomical clock. You can forecast the flow at a given site years, even decades ahead. That makes tidal one of the few renewable sources you can genuinely plan around. So why isn't it everywhere already? Well, the catch has always been speed. A conventional tidal turbine is basically an underwater windmill bolted to the seabed, and the power it makes rises with the cube of the water speed. Double the flow and you get 8 times the power. That cubic math means these turbines only pay for themselves in very fast water, above roughly 5.5 miles per hour. And sites that fast are rare. They are a handful of violent channels and narrow straits, and most of them are already spoken for. The vast stretches of slower coastal current move at a gentle walking pace. They were simply not worth the steel it would take to harvest them, and that is the barrier that kept tidal from ever being a serious player in the renewable mix. Minesto's answer to this dilemma came out of an unlikely place. The company was founded in 2007 as a spin-off from Saab, where an engineer had been working on a turbine concept and realized something useful about water. Because water is nearly 1,000 times denser than air, the energy in a slow current is far more concentrated than it looks. You could fly through it the way a stunt kite flies through the wind. And that idea is at the heart of this design. The Dragon 12 is a wing about 39 feet across, weighing 28 tons, tethered to the seabed by a single cable. Hanging beneath the wing is a turbine and a generator, and the whole thing is held down in the current like a kite on a string. When the tidal stream flows past, the wing generates lift, exactly as an aircraft wing does in air. An onboard control system then steers the kite through a continuous figure 8, sweeping it back and forth across the current. And here is the clever part. By flying crosswise instead of sitting still, the wing moves through the water several times faster than the current is actually moving. Minesto says the kite can reach up to 8 times the speed of the surrounding flow. And if the turbine is moving through the water several times faster than a stationary one would, the power it can pull jumps dramatically, even though the current itself is weak. The kite is essentially manufacturing its own fast water out of slow water. That is what lets a small turbine, just 11.5 feet across, do the work of something far larger. The whole machine is anchored not by a heavy slab, but by a single drilled-in foundation on the seabed, which keeps the footprint small and the install quiet. The electricity travels back down the tether through a power cable, then along a seabed line to shore. The wing flies, the turbine spins, and the weak coastal current that no other machine could use turns into grid power. In February 2024, in the Vestmannaeyjum Channel in the Faroe Islands, the Dragon 12 fed its first 1.2 megawatts into the national grid. That is enough for around 1,000 homes. It made this the first megawatt-scale tidal kite ever to deliver power to a grid. Set the kite against a standard seabed tidal turbine, and the contrast is mostly about weight and reach. A conventional turbine needs heavy structure and very fast water, which restricts it to a few rare sites. The kite generates its own speed, so it can work in slower currents that cover far more of the world's coastline. Minesto's own estimate is that this approach could more than double the tidal resource worth exploiting. Other tidal players, like Orbital Marine Power with its floating O2 platform, still depend on those rare fast water sites, which leaves most of the world's coastline out of reach. A Dragon 12 weighs around 28 tons and breaks down to fit inside a standard shipping container. It can be installed from a single, modest boat and a seabed anchor, with no giant jack-up vessel and no massive foundation. That lightness flows straight into the cost, because less material and simpler installation mean cheaper power. The honest comparison, though, is against offshore wind, which is the mature option most coastal grids reach for. A single Dragon 12 makes about a third of what one large offshore wind turbine produces, so on raw output, wind wins per unit. But the Kite's pitch was never raw output, it is the predictability, and the fact that it reaches water where wind platforms cannot be built. On price, Minesto projects a levelized cost of around $108 per megawatt hour once it has 100 megawatts installed, falling toward $54 as it scales. For commercial arrays, the company targets roughly 6 to 8 cents per kilowatt hour. That is still above the cheapest solar and wind today. But it sits in range of offshore wind, which the US Department of Energy pegged at about $89 per megawatt hour in 2022. The timing of this solution matters because the value of predictable power is climbing fast. As grids pack in more solar and wind, the cost of smoothing out their swings keeps rising. Operators pay for spinning reserves, for backup gas plants, and increasingly for big banks of batteries, all to cover the gaps. There are even stretches when solar and wind flood the grid at once, prices crash below zero, and operators have to pay to shed power they cannot use. A source that delivers on a known schedule sidesteps a lot of that. It shaves balancing costs down, and that hidden saving rarely shows up in a simple price per unit comparison. Tidal also tends to peak at different hours than the midday solar bulge, so it can fill in around the renewables a grid already has, rather than piling onto the same glut. There is also a hard geographic advantage to all this. Remote island grids and isolated coastal communities often have no cable to a neighbouring country, so they lean on imported diesel and pay dearly for it. The Faroe Islands are exactly this case, and they have committed to running entirely on renewable power by 2030. A predictable local source that fits their fierce tidal channels is worth far more to them than the bare cents per kilowatt hour suggests. And the wider scale potential for this is significant. The US Department of Energy estimates that tidal energy, if fully developed, could power on the order of 21 million American homes. That is the single biggest reason that keeps drawing money and attention back to a technology that has spent decades stuck in the lab. For all that promise, the Kite has serious ground to cover, and the first obstacle is geography. It still only works where there is a decent coastal current. Inland grids, calm coastlines, and most of the planet's landlocked population get nothing from it directly. Tidal will be a regional contributor, strong in the right places and absent everywhere else, not a universal fix. But the harder problem is the sea itself. The ocean is brutally hostile to hardware, and tidal history is littered with machines that the water destroyed. One earlier turbine deployed in the Bay of Fundy had all 12 of its blades torn off within 20 days by currents stronger than it was built for. Saltwater corrodes, marine growth, fouls moving parts, and the constant flexing wears at every joint and bearing. The Kite is lighter and simpler than a bolted-down turbine, and its tether faces less stress than a floating wind platform. But it is also a moving aircraft flying thousands of loops underwater, and moving parts are the ones that fail. What would settle the question is years of real operating data showing the Kite holds up over time. Servicing, at least, looks manageable so far. Minesto recovers the Kite for inspection by towing it back to shore with a single small workboat, latching onto the seabed foundation through a remote connection that needs no divers and no underwater robots. The company says a full launch or recovery takes under 2 hours. Its first unit has logged months of grid-connected running and come back ashore for maintenance, which is encouraging, but a multi-decade track record is still being written. Then there is marine life, the concern regulators raise first. A turbine spinning in a channel where seals, fish, and diving birds feed looks, on its face, like a hazard, and that fear has stalled permits across the industry for years. The reassuring news arrived in early 2026, when a US study watched more than 1,000 interactions between sea animals and a small tidal turbine. It recorded 0 collisions with seals or seabirds and a 98% safety rate for fish, with seals actively swerving away from the moving blades. Now, that study used a small stationary turbine, not a flying kite, so it doesn't give us much understanding on the impact Minesto's design will have. The swooping motion of a kite raises its own questions that will need their own monitoring. But it is the strongest evidence yet that marine animals can sense these machines and avoid them, and it points a way through the regulatory logjam. The roadmap from here is about going from one kite to many. Minesto's next step in the Faroe Islands is the Hestfjord Dragon Farm, a first-of-its-kind array of 6 upgraded Dragon 12 units totaling 10 megawatts. Beyond that, the company has mapped a 200 megawatt build-out across 7 sites in the islands, enough to supply around 40% of Faroese electricity at an estimated cost of 400 million euros. The engineering is still improving in the water. In 2025, Minesto found that fitting a longer tether lifted the kite's power output by about 25%, a gain that fed straight back into the business case for the larger farms. Each operating month is teaching the company how to wring more out of the same wing. Minesto is studying powerful ocean currents elsewhere, including the Gulf Stream off the United States, where steadier flow could push capacity factors and costs in the right direction. For decades, tidal power had a reputation as the renewable that was always promising and never quite arriving, held back by the fact that only a few violent channels ran fast enough to bother with. What Minesto changed is the speed requirement itself, turning a slow current into a fast one by flying through it, and that quietly hands the technology a far larger map to work with. But real challenges with this tech still remain. It only works at the coast, the ocean punishes hardware, and the long-term reliability and the wildlife questions still need years of data behind them. But there is now a megawatt-scale kite feeding a real grid, a clear path toward full arrays, and a kind of power that the moon makes dependable in a way no cloud or calm spell can disrupt. If you want to keep up with the technologies reshaping how we power our homes, follow along and keep watching, because we will be tracking the ones that matter as they move from a single prototype to the grid.